Thank you for the invitation to speak here. Is this on? So this is a combined higher structures and operads meeting. So I try to find a subject in the intersection of these two themes. So we will have another talk about operads, but higher operads. At the same time, I should perhaps apologize because it will be a rather technical talk, I'm afraid. There's nothing I can do about that. Well, we can all recover during the dinner or during a drink before that. So there are various ways to, by now standard approaches to theory of higher categories, motivated by homotopy and homotopy between homotopy and so on. And one is to work with Rask's complete Siegel spaces. And the other is to work with categories enriched in simplicial sets, but these are usually just called simplicial categories, somewhat ambiguously. Or an alternative framework is that of infinity categories, also known as quasi-categories or weak CAM complexes or inner CAM complexes. And in some sense these approaches are equivalent, but this is the simplest one because this is really the category of simplicial sets, but with a model structure a little different from the classical one, so the Joyal model structure. So these are vibrant objects in the Joyal model structure. And I can tell you exactly what they are. They are like CAM complexes. So vibrant objects, can I squeeze in a letter somewhere here? X, such that X has a lifting property with respect to horns. But only for 0 less than I less than n. So for n equals 2, there's a familiar picture. If you have two edges in a simplicial set, you can find some composition. And this composition is unique up to homotopy. So it's some sort of weak kind of higher category, where you have a weak composition. So you can read all about infinity categories by studying the 2,000 pages of Jacob Lurie. Where you see how well this works and how convenient it is to work with these infinity categories. But this is a conference on operads, so one can ask oneself, what should be an operad in this context, in this weak context? What is an infinity operad? Okay, if you take the middle of these three hyphens, then you could just say it's a simplicial operad and try to work with those. But the main disadvantage of simplicial categories is if you want to work with them homotopically or want to derive constructions, is that there are very few cofibrant objects. The cofibrant objects have to be extremely free, and as soon as you do construction, just simple like taking the product of two categories, for example, you lose the freeness. And it gets much worse with simplicial operads. So it's exactly the problem that we discussed during the previous talk. Tensor product of operads are notoriously bad. And so that's not so good to work with. But there are various approaches in the context of infinity categories which work much better. So I want to compare, as the title said, I want to compare two of them. So one is Lurie's definition of infinity-operad based on the category of simplicial sets over the nerve of a category which I will try to call F. F is a category of finite sets, possibly empty, and partial maps between them. So you all know this category. Maybe you know it in slightly different guises. You may know it as the category of finite pointed sets and pointed maps, but if you take out the base point, and it's a bit inconvenient to carry the base point around for an hour, so I will do it like this, you get finite sets and partial maps. Or if you take the opposite, you get Siegel's category gamma to study infinite loop spaces. So this is somehow building on simplicial sets, and simplicial sets with this Joyal model structure. And the other approach is via dendroidal sets. So dendroidal sets are also some extension of simplicial sets. Many of you will have heard me talk about this before. And the Joyal model structure on simplicial sets extends to one on dendroidal sets, and the fibrant objects here are the dendroidal infinity-operads. So for today, I will to distinguish the two sides, I will talk about Lurie-style infinity-operads and dendroidal infinity-operads. And they both occur as the fibrant objects in the model category. This is in some sense building on the Joyal model structure, and this is in some sense analogous to the Joyal model structure. So one is sort of an extension in the vertical direction and the other in a horizontal direction, which I hope to make a bit more clear during the talk. But the theorem that I would like to explain, at least a little bit, and I should not forget to mention that this is joint work. I'm sorry. With somebody that Ezra will tell you how to pronounce the name of, and Gijs Heuts. These are two vowels which are typically Dutch. Anyway. This might be easier for some of you. So Gijs was a student of mine at Utrecht, and he is now doing a PhD at Harvard. And Vladimir finished his PhD a while ago. So there is a equivalence between Lurie's model category for infinity-operads and the dendroidal one. So in some sense this perhaps doesn't come as a surprise to you, because already I think in the first installments of derived algebraic geometry and higher algebra of Lurie, he conjectured that this was the case. But that's quite some years ago, and it took us a while to find the proof. Now, so that's nice to know. It's particularly nice to know because because these models for infinity categories that I mentioned here, simplicial categories and RESC complete Siegel spaces, have dendroidal analogs. So immediately from this equivalence, you get further equivalences of the Lurie category with that of simplicial operads, or topological operads if you like, or some version of dendroidal version of complete Siegel spaces. So in particular, as a corollary, every Lurie infinity operad is weakly equivalent to one coming from a simplicial operad. So I read this as some sort of strictification theorem. See, a simplicial operad, in a simplicial operad you have nice composition of operations and they're associative on the nose and so on. And in the Lurie operad you don't even have the compositions, you have to choose them, and they are only associative up to homotopy and so on and so forth. But you can always strictify such a more flabby object. Of course the flabby object has other nice properties. It's small and it is cofibrant automatically. The other application related to this is that it gives a good derived tensor product on each of these categories, because the dendroidal model category, which I wrote down somewhere, here, this is in fact a monoidal model category. So although the tensor product of operads is extremely badly behaved, as far as we know, the tensor product of infinity operads in the dendroidal sets is extremely well behaved. Okay, there's a very simple definition which sort of imitates the Boardman-Vogt definition that we saw an hour ago. I don't think I will go in detail in that direction, but so using this you get some results of Lurie, for example the Dunn-style theorems that Lurie calls additivity theorems about tensor products of EN operads, EN and EM operads. You can pull through this equivalence and get nice small combinatorial models for EN operads just by tensoring in dendroidal sets, taking tensor powers in dendroidal sets. Okay, anyway, these are just two examples of some sort of transfer between these two kinds of models and what is known about them. Okay, so I will begin the talk by explaining in a little more detail these two models. And politeness forces me to start with Lurie, but this will take quite some time. It's not entirely my fault. Okay, so So I will use the lingua franca, as it has been called, of colored operads. So if P is a colored operad, I will give a simple construction for colored operads in the category of sets, if you like, and then the analog state some properties of it, and the analogous properties up to homotopy will give Lurie's definition of infinity operad. Okay, if P is a colored operad, we can make a category which Lurie denotes P tensor, equipped with a map to F. And the construction is quite simple, and I think many of you will have seen it. So the objects are sequences C1, Cn, which I will maybe write C underlined, of colors, and let me give this map a name. So these objects are mapped to just a set of indices, to the set of n elements. Okay, pi with pi of c equals n, which is the set 1 n. Okay, and then the arrows are between two such objects, C1, Cn, to D1, Dm, are pairs, alpha P, and alpha is a map from n to m in F, so it's a partially defined map of finite sets, and P is a sequence, P1 up to Pm, where Pi is an operation of the operad, which has Di as output, and it takes the inputs which are mapped by alpha to I, and I will write this sequence as the sequence C alpha inverse I. So I hope this is clear. So the sequence of CJs where alpha j equals I. So you see that these operations, these PI, they only use a part of the data, and there may be colors here that are never used at all. So this makes sense for a partial map alpha. Okay, and this is a category. The composition is defined in using the operad composition, and the projection pi is the obvious one, just picking out alpha. Okay. So this category, together with its functor to pi to f, has some simple properties. Basic properties. One is that if you have an arrow in F which just forgets a few elements, so it's like a partially defined identity map, and these are called inert maps, then there is a canonical arrow lifting it in this category P tensor just by using the identity operations of the operand. Okay, so if alpha from n to m is inert, i.e. alpha inverse of j is one element, okay, the easiest way to think of these maps is you think of M as a subset of N, okay, and the alpha is defined on that subset as the identity, and it forgets the other elements. Is inert then for any C over N, there is a over N, there is a canonical lift, which I will denote C alpha tilde alpha shriek C in P tensor. Okay, and this arrow has a special property. It is a co-Cartesian arrow, which is co-Cartesian. So this means if you have a map here and you have a diagram, a commuting diagram, like you have a factorization down in F, you can find a unique factorization here. Okay. In particular, if you have a further such, you can find one here for the composition, and you can find one for this triangle, and everything by uniqueness, everything will commute automatically. Okay, and you can put any string C, D, E, F, and so on there, and I will use pictures like this when I move to the Lurie's definition. So that's co-Cartesian. So this functor from P tensor to F, it looks a little like a co-fibered category, if you're familiar with that, but it's only a co-fibered category over the inerts. Yeah. So I like to think of this as these co-fibered categories with chosen liftings. It's a little bit like a flat connection, but now you have a flat connection only over some arrows, which is quite familiar in geometry too. It's called a partial connection. It plays a dominant role in variation theory. Okay, so that's the intuition. And if you have these lifts, then in particular, if rho I from M to 1 denotes the inert, which only remembers I, so it's undefined except at place I, then, let me erase this picture. Then, if you look at the arrows in P tensor, which lie over an arrow alpha from C to D, then it's the same as having for each one up to for each I from 1 up to M an arrow P tensor rho I alpha from C to rho I shriek of D. Okay, which is this is just DI. Or did I call it J? Anyway, if I did it correctly, I'm just copying the definition of morphisms. There's nothing going on here. And thirdly, you can look at the fibers of this partially co-fibered category. So all the arrows that are mapped to the identity, and if you take the fiber over an object n, you can project away using these alpha shrieks. To P tensor 1, and this is an equivalence of categories. Yeah. What you should remember about this condition is that if you have an n-tuple of objects over 1, you can put them together into a sequence of which is a single object over n. Okay? This is surjective up to isomorphism in particular. Okay. So now, let me try to erase this a bit further. So now, Lurie rephrases this in the language of infinity categories. So a more homotopy invariant definition of Lurie infinity-operads is a simplicial set. Let me just call it X. So X plays the role of P tensor, equipped with an inner vibration. So not a can vibration, but a slightly weaker kind of map. A map satisfying a slightly weaker kind of condition, namely having this lifting property only for inner horns. It has disappeared from the board, I think. X to nerve of F. Again, call it pi. So this implies that X is also an infinity category, such that, and now 1. For every vertex V in X, now let me call it C, in Xn. So now you have to be careful not get confused. There actually have two indices, namely the fiber of pi over which it lies and the simplicial degree. So this refers to the nerve of F. Any vertex C there and any inert alpha from n to m. There exists a co-Cartesian edge C alpha shriek C. So this is a one simplex in X, not in X, so in X1, and pi of it over alpha. Pi of it is alpha. Okay? Just existence. Now, perhaps you don't know exactly how to phrase what co-Cartesian in infinity categories, but it's exactly the same diagram that I so cleverly erased. But let me remind you of a diagram. So for an inner vibration, I can put an index here, except 0 and n. But sometimes I can put the index 0 here, as long as this n simplex starts with a co-Cartesian guy. So an edge act in X is co-Cartesian over its image here, if you have a filling condition like this for every n. But really, if you write it out quasi-categorically, you find the same diagram. Okay. 1. 1. So 2 was saying something about the arrows, and I will write something in exactly the same form, but now I will use the notation map. Map in X over alpha between C and D to pi I equals 1 to m map X rho I alpha C alpha shriek D, sorry, rho I shriek D is a weak equivalence. So what does map mean? If you have any infinity category, you can look at its path space. It will have evaluation at the endpoints, and then if you have two vertices, let me write delta 0 here. If you have two vertices, you can take the pullback, and that's map xy. Okay, so it's a simplicial set. In fact, it's a Ken complex, although X is only a Ken complex in the weak sense. So this is going to be a weak equivalence or a homotopy equivalence of Ken complexes. So that's condition 2. And condition 3, where is condition 3? It says something about the fiber. The fiber of X over N. That's the simplicial set, which is the inverse image of this vertex to the product of fibers 1 up to N X1, given by the rho I shrieks, is also a weak equivalence. Okay. Now this condition looks, if you want to work with this with these conditions, I think you might be misled by the fact that they look more innocent than they actually are. Because in number 1, I choose these co-Cartesian lifts, and I use these to construct simplicial maps, for example, from xn to x1 by induction. So these operations, these two operations are only defined up to homotopy, and they depend on the choices made in 1. Okay, but the conditions, of course, are invariant under the choice.
These fibers from the condition that pi is in inner fibration, what do you learn about the vibrancy or lack thereof of
they are just infinity categories.
Oh.
They're not the cap, but they are.
So when you say weak equivalence, you mean in which sense?
Yes, that's a good question. I'm sorry. So is an equivalence of infinity categories.
Ah, okay.
Thank you. Right. So the theorem of Lurie these infinity-operads are the fibrant objects for a model structure of, well, I would like to write simplicial sets over the nerve of this category of finite sets, but in fact, to get these, to be able to work with this co-Cartesian property conveniently and code it up in this model structure, you need simplicial sets where you select a set of edges, a set of one simplices. It's called marked simplicial sets. Okay. Okay, but now I'm taking a slice category over an object which is not yet in the category. So I have to tell you which edges to mark here. And I mark here exactly the inerts. In the nerve of F, mark the inerts. Good. So maybe one of the main sources of examples of these things is that if you start with the simplicial operad, you can take something like the homotopy coherent nerve, and if the simplicial operad is sufficiently nice, its home spaces are Ken complexes, then this will give you such an infinity operad. Okay, so maybe I'll write this somewhere just to keep in mind. Examples come from homotopy coherent nerves of simplicial operads. Good. So now I have 25 minutes to.
Oh, yeah, sorry, we took time.
Did we start a little late as well? Okay, now the other side. So dendroidal infinity operads. So many of you have heard me talk about this before, but the starting point is that you extend the category delta of simplices to a category omega of finite rooted trees. Okay, and I call this inclusion I. So tree could look like this. I'm labeling the edges. So this tree has a root, which is A, and it has leaves, which are edges without a vertex above them. They're like inputs in an operad, for operation in an operad, and vertices. And now the arrows are generated by faces and degeneracies, exactly like in delta, except that there are also automorphisms of trees. So arrows generated by degeneracies, inner and outer faces, and isomorphisms of trees. And this inclusion I of a simplex is just this linear tree with edges numbered 0 up to n. Okay. Now let me say a little bit more about the arrows, or at least about the faces. So what you can do is you can chop off a vertex on top. So let me also name the vertices maybe. U, V, W, P. So you can take the face which chops off V. So the result will look like this. Or you can contract an inner edge. And you will the domain of that map will be this tree. So E has disappeared, the root is the same, and these are F, G, H. So this is an outer face. And this is an inner face. Or you could also chop off the root here, because there's only one inner face above the one inner edge above the root. So you could also what will it be? E, F, G, H, A, delta U, or maybe delta A. So there's also an outer face, outer face, outer face, inner face. And if you draw these pictures for a linear tree, you will recover exactly the usual simplicial faces, where the outer faces are d0 and dn, and the inner faces delete one of the edges in the middle, but you can think of that as contracting that edge.
One of your arrows looks like it's disoriented. Is that right? Or did you intend to orient the arrows?
Looks all right to me.
Oh, you've done more than one. I'm sorry. Yeah.
This is the orientation is right.
Yeah.
Okay. So now you can do lots of things exactly like for simplicial sets. If you work with set value presheaves on omega, so the category of dendroidal sets is sets to the omega op, and simplicial sets is of course sets to the delta op. And this inclusion induces some functors here, I upper star and an adjoint pair of functors. So you can use dendroidal sets as some extension of simplicial sets in some very precise sense. And so there is a model structure theorem that I proved with Szynski. There is a model structure on dendroidal sets. So I abbreviate this as these sets, whose fibrant objects are exactly the dendroidal inner count complexes, alias dendroidal infinity-operads. And so I will tell you what these are. Maybe I can write it here. If you have a presheaf on this category of trees, and you have a given tree T, you can form the boundary of this tree, delta T, and which is the union of all the faces. And inside that boundary, you could take a horn. And you could ask for a lifting property like this for any tree T in omega and any inner edge E, where lambda E T is union of all the faces except contracting E. Okay, so where is my picture? I don't know whether I made a clever picture for this example, but maybe lambda E of this tree consists of this bottom part and this top part, but it omits this face. Yeah? So it's just a union of two faces in this case. So it looks very much like this definition of infinity category, except that I take a category, an index category, which is slightly bigger than delta. And this is a very nice model category. It is monoidal for a Boardman-Vogt style tensor product, and it extends exactly the Joyal model structure. So if you take a simplicial set and you view it as a dendroidal set using I-Shriek, it will be fibrant in the Joyal structure if and only if it is in the dendroidal structure. And lots of things can be translated between these two. So, how can we compare these? So, the Lurie category is, of course, also a category. If I forget the markings a little bit for just for expository purposes, then Lurie's category simplicial sets over nerve F, with no markings, is also a pre-sheaf category. With representables simplices delta n A the nerve F. So these are sequences of finite sets and partial maps. A0, A1, AN in F. Okay. Now, if you have such a sequence, you can draw it almost as a tree. Okay, but there is a bit more structure there. So that's an obvious observation. So such a thing, such an A, can be drawn as a forest, as a sum of trees. So, for example, if you well, let me draw. So here is a typical simplex. You map, if you can read it, a 6-element set to a 4-element set, to a 3-element set, to a 2-element set, and then here there's something undefined. So you see you have a forest, you have a disjoint juxtaposition of trees, but some have their roots at a higher level because you can forget. And some have their leaves not at level 0, and I already indicated that I'm going to put a bullet there, so I'm going to put a zero-ary operation there. Yeah? So it looks very much like a sum of objects in omega. Now, so it is like a sum of objects in omega. But there's something a little bit strange in this on this Lurie's side. Namely, if you take the vertex, which is the empty set, then you will get the empty forest. Yeah. So delta 0 maybe I call it 0 NF gives the empty forest. So there is a point in this Lurie category which homotopically on the dendroidal set side has completely disappeared. It also disappears on the Lurie side because I didn't tell you much about the model structure, but in fact the map from the empty set to this representable object will be a trivial cofibration for Lurie. Okay. So and the other difference, big difference is the markings. Okay. So to bring these two, so in hindsight, it looks maybe relatively obvious, but to bring these in line, these two the Lurie model category and the dendroidal category in line, we construct. Maybe the easiest thing is just to draw a big diagram on the board with all the model categories, intermediate model categories. And left Quillen equivalences between them. And the diagram looks as follows. So here's dendroidal sets, and here is Lurie's category. Marked simplicial set over the nerve of F. So how am I going to relate these? Well, first of all, I'm going to extend omega to forests. But I'm not going to add a close omega on the direct sums. I will tell you in a minute, if Ezra gives me a minute.
I'll give you a minute.
Thank you. How to do it? And there will be an obvious functor here, and one can prove it's a left Quillen functor. That's easy, but it will be a bit hard to show that it's a left Quillen equivalence. And what we do is we go to dendroidal complete Siegel spaces. And forestial, so to speak, complete Siegel spaces, completely analogous. And there will be left Quillen equivalences here. This is a known one. It also occurs in the work with Szynski, and one can prove that this is an equivalence.
The word is silver.
I won't tell you how much time I spent with Hinich talking about Greek and Latin words for forest. And I know that this is not a word. Right. Okay. Then so this takes care of these sums. Then the other very easy thing to do is that you can force that vertex which is a little bit in the way somehow to become the initial object just by looking at the category under 0, and there will be a functor here which just takes an object and sums it with 0. You add a disjoint base point, as it were, but since this base point is homotopically empty, I'm sorry, this is going to be Quillen equivalence. Okay. Now, good. Now we need to take care of the markings, because on Lurie's side you cannot manipulate anything if you don't take the markings around. So there are versions of this with markings, and in fact, Gijs Heutz developed this in quite a general context when he showed that for example, the category of infinity algebras occurs as a localization of dendroidal sets. He works with a version of this marked dendroidal sets. And let's see, what is the left functor? The left functor is sort of a minimal marking. That's a Quillen equivalence. And then here you have a similar functor, U upper star.
Sort of like stuff marked degenerate one synthesis, or
exactly.
Yeah.
Well,
More. Yeah.
mark degenerate one simplices in trees, not in arbitrary trees.
Yeah.
Okay, or forests. And now you can do this construction. So I call this picture omega of A, and I view it as a sum of trees, exactly the way I depicted it. And omega, okay, maybe I will not destroy the instructions of Kuno. Maybe I'll look up, let's find this. So omega from delta over the nerve of f to f sets induces functors omega f sets. Let me try to keep the same direction. Lurie. So here is a functor which we call omega shriek. It's just a can extension of that functor. And it has automatically has a right adjoint, but you will see that this right adjoint automatically has is a pointed object over 0. So it automatically lands here. Okay? And the advantage of going here is that it will have a further right adjoint, which is not the case here. So if you view it here, it will again be a left Quillen functor. So I can put it in the diagram. So that looks like a bit of a silly thing, but it's sorry, everything should be marked. Omega shriek, omega upper star. Okay, and then the work, which unfortunately I really do not have any time to explain, is to prove that these two functors are left Quillen. Okay, and the main job is to prove that omega shriek and omega upper star are left Quillen, i.e. send trivial cofibrations to equivalences. Yeah? And just to give you a little bit of an idea of what this omega upper star looks like, let's just evaluate it on a tree. Omega upper star of a tree, let's take a small tree, will have simplices, will be the union of simplices of the following kinds. Let's label the A, B, C, D, E. You see, there are so I will write down simplices whose edges are elementary in some specific sense. The edges involve only one operation at a time. But the operations, you have to be careful what the operations are. The operations can be vertices in the tree, or they can be the act of forgetting a color, or they can be a permutation. So a typical simplex will look like this. Here is E. Here is, for example, D, C, and then you could put an operation here. And okay, if I forget, then I should do nothing here. I should only do one thing at a time, and then I could forget E, for example, and then I continue like this, and then I forget, what is it, B, and I end with the empty set. So this is a 0, 1, 2, 3, 4 simplex. Okay, and if I put the name A back, yeah, you do one thing at the same time. But of course, the classifying spaces of symmetric groups are all included in omega upper star of the smallest trees. So these are quite big simplicial sets. And now you have to prove that, for example, these inner horns that you have here are being sent to trivial cofibrations on the Lurie side. And that involves lots of combinatorics of trees. So if you ever look at the paper, you will see that it unfortunately takes up quite some spaces and quite some pages and some ingenuity of the young, of which we had one. Okay, so maybe one last remark about the proof. Of course, as many of you will know, none of these categories really have a set of generating trivial cofibrations, a canonical set of generating trivial cofibrations. That's why I corrected myself and I said canonical.
Okay.
Yeah, a handable set of generating trivial cofibrations. But to check whether something is a left Quillen functor, you can work with a set of trivial cofibrations which is generating in a much weaker sense, because you want to check whether its image is a weak equivalence. And weak equivalences are closed under 2 out of 3. So if you allow yourself as operations for generating not just push-outs and compositions, but also 2 out of 3, there is a very specific generating set. In dendroidal sets, essentially, it are the inner horns. On the Lurie side, it's what he calls the p-anodynes, and one can work with those. But to explain you how this works, would have to take some more time. Thank you.
Thank you. Jesse?
This is just a small question, but you mentioned that the fibrant objects in your model structure with Szynski were sort of inner Kahn dendroidal sets. How should we interpret a Kahn dendroidal set? What kind of operad is that?
That's a good question. So there are various localizations of dendroidal sets where you try to add some of these horns for other faces, and so the first one you get is infinity algebras. Then you can go to connective spectra, and then you can put a group line condition. And this is work of, so the first step is work of this same student of mine, Gijs Heuts. And building on that, there's Mattia Basic and Nico Roos from Regensburg have worked out these localizations. So dendroidal sets contains all the combinatorial information to do at least connective spectra, for example.
Any other questions? All right, let's thank the speaker. Okay?